Welcome to the Picture Language Seminar. Today, we're very happy to have Bruno Nachtergaele. Bruno got his degree in Leuven in 1980s, went to Princeton and collaborated with Elliot Lieb, and for many years has been in UC Davis. He's going to tell us today about dimerization and quantum spin chains. And yes, well, share your screen, Bruno.
Here it is. You should be seeing it right now.
Yeah.
Okay. So, yeah. So the specific topic is dimerization, and that's about recent work with Jakob Bjoernberg, Peter Muehlbacher, and Daniel Ueltschi. And but I will spend some time placing this into context. So why this is an interesting question, and why now, and what's the particular challenge that we addressed in this problem. There will also be some very brief mentioning of related work that sort of focuses on another aspect of this problem with Robert Sims and Amanda Young. Okay, so let's dive in. So here is an outline. It looks like quite a bit of topics, but I think I will definitely try to explain how they all fit together and how they motivate each other. So I'm sure most of you have heard about spin chains. It's an old subject, and so let me very briefly say what it's about, and in particular in the context of what I want to talk to you about today. And then I will start by sort of describing the state of affairs for a class of spin chains, the spin-1 chains. They're often referred to as the bilinear biquadratic Hamiltonians, or spin-1 chain. It's been a topic that many people have studied from different angles, and played a very important role in sort of the general development of the theory in more recent decades. Then I will tell you what dimerization is, in case you don't know exactly what we mean by this. So this will be very short. I do a little aside on symmetry protected topological phases and stability, which is sort of the wider picture. The theory of many body systems on a lattice, of which quantum spin chains are, if you want, the simplest case, is a topic that is really blossoming right now, and this is one of the reasons. Then the EKLT chain, which is a very famous model and is an example, is one point in this family of bilinear biquadratic spin chains. So I will explain how you can generalize it, and in a way that you see that you could generalize it in different ways, and different ways are interesting and will sort of motivate the introduction of a family of spin chains with ON symmetry that people have looked at, and look at the phase diagram of that family and see what we know and what we still don't know. And then I will mention the main results of this work with Bjoernberg, Muehlbacher, and Ueltschi, sort of the new information that we've been able to add recently in a preprint that appeared earlier this year. Then I will discuss how we go about it. There's many different mathematical techniques that people have developed to study quantum spin chains, and they're sort of quite different. In this case, we use a graphical representation and analysis of that. I will explain that. It has a nice touch that I will be able to show some pictures, which Arthur likes a lot in his seminar. So, so this will be good. Then I will discuss, if there is time, some other spin chains that can be studied in a similar way, and we will see how far we get to that. Okay, so spin chains. Simplest setting, we will always work with finite spin chains, and of course, we are interested in the thermodynamic limit. We want to know what happens when the length of the chain goes to infinity. But to formulate things mathematically and to start with simply defined and well-defined objects, we start with finite chains, and they're going to be translation invariant. So we're going to have a finite dimensional Hilbert space at each side, and I will have as many copies as I have sides in the chain. So that is the Hilbert space here. I'm going to consider the family for all non-trivial dimensions. So that n will be the dimension. It's related to the magnitude of the spin, of course, by this relation that you know very well. The half integrable value s is related to the dimension by this relation 2n plus 2s. Aha, that's very good. I wrote this wrong. So n is 2s plus 1. So I need to switch these around. Very good. So this way I keep myself awake. So as I said, we will study only translation invariant models, and in fact even only nearest neighbor interactions. So what that means is to define a model, we just pick a salvage-owned element in the tensor product of two copies of the n by n matrices, which is just an operator on if you want a spin chain of two spins. And then we define the Hamiltonian by placing this nearest neighbor interaction everywhere in the chain and summing it up, and we get the Hamiltonian. And we are interested in ground states. So that means the eigenvectors belonging to the bottom of the spectrum, the smallest eigenvalue of this big Hermitian matrix. So, so quickly, a few examples written in sort of the familiar way that they appear in the physics literature in terms of spin matrices. So if you have the n by n spin matrices that generate the n-dimensional irreducible representation of SU2, so they are proportional to the Pauli matrices for n equal 2, then you have 3 by 3, 4 by 4 spin matrices, and so on. Then the Heisenberg model is the model where this interaction, there could be a coupling constant, could be a different sign, but it's sort of S dot S. It's this dot product of the spin matrices, just these three terms, which is invariant under the irreducible representation of SU2 that you have acting on each of the spins. So that's sort of the basic model. That's the very first one that was introduced by Heisenberg. That's the one that people have studied for a long time, that inspired Bethe to introduce the Bethe ansatz and so on. It's been a very long history. A very important and very interesting model with three-dimensional spins is the AKLT model. I'll say more about it in a second. It was introduced by Affleck, Kennedy, Leap, and Tasaki. And I'll explain why. And it really played an enormously important role in the development of our understanding and the theory, including numerical methods and all kinds of things. I won't be able to go into all of that, but here is the interaction. It's again a nearest neighbor interaction. It's also SU2 invariant. And it has this Heisenberg term, but then also the square of it. And obviously that also commutes with SU2. And in fact, if you look at it closely, you see that this is an orthogonal projection. And in fact, the orthogonal projection on the spin two states of two spin ones. So the energy of parallel spins, which would make the spin one variables add up to a spin two, is given as 1, and then the complement, the orthogonal complement, is energy 0. So it has an antiferromagnetic nature. The ferromagnetic states are given high energy. And then when you see that, then you can ask why adding this term, and we'll get to that in a second. And if you add this, then you can as well consider the case where you have arbitrary coupling constants in front of these two terms, the Heisenberg interaction and the square of the Heisenberg interaction. And that turns out that's the most general isotropic nearest neighbor interaction for a spin one chain that you can have. But surely you can multiply by a positive constant, you can rescale everything, you can also add a constant, but that doesn't change anything about the ground states. And therefore, this is the most general interaction in that case. So let's look a little bit more in detail to that family of models. And since I parameterize the coefficients here by an angle phi in anticipation of drawing this phase diagram, it's often represented this way because it removes this additive constant and then positive, typically scale factor, and so everything is nicely summarized on a circle, or sometimes a disk, but it's really just an angle. And let's look at some special points. Well, first of all, we have here phi equals 0 at this point. Here is the Heisenberg chain that I just introduced. And what's interesting about that is that although it had been around for almost 100 years, Haldane conjectured, that he will say explained, discovered something really interesting about the spin 1 chain, namely that it behaves very differently from the spin 1/2 chain. And you know, people always work with spin 1/2 spins, and they know about the classical limit. And it was really a surprise that the behavior of the ground states of this model would depend essentially on this dimension n, the spin dimension, whether it's even or odd, in fact. There's a topological effect that Haldane discovered, and that is really the start of topological phases in spin systems. So what he found is that at this point, you have in the thermodynamic limit a unique limit. You're interested in infinitely long chains, and it's a disordered state with a finite correlation length, and there is a spectral gap above the ground state. So excitations have a minimum positive energy uniformly in the length of the chain, and in particular in the infinite chain. And that's in stark contrast with the spin 1/2 chain, where people have solved exactly starting with beta, where you also have a unique state, but it has power law interactions, and the spectrum is gapless. And so Haldane conjectured that, in fact, these two cases alternate as you go in increasing dimension over even odd dimensions of the spins. It's all spin chains. So space is one dimension, but the spin dimension is what matters here. So that's very interesting. It was surprising, and people tried to prove it. And it seemed to be harder than you might at first have thought. It's not an exactly solvable model. And so this is why Affleck, Kennedy, Leap, and Tasaki had this idea of, well, if there is this phase, and Haldane, in fact, had a theory about that these are not just things that occur in very special points. There is a phase, and I have sort of indicated here by using the same red color to indicate that entire segment of the disk. There's you can vary phi a little bit, and you should still have the same properties. And so then Affleck, Kennedy, and Tasaki had the brilliant idea to look at this model where you exactly have this combination, this choice of angle, where you have this projection as the nearest neighbor interaction. Turns out that's a frustration-free model. That means that the ground state is actually simultaneously an eigenvector with the smallest eigenvalue of all the interaction terms. And these interaction terms don't commute, so this is a non-trivial property. It also doesn't mean that it happens for other states, but the ground state has this. So that is what is called frustration-free, and I will come back to that a couple of times. There is an exact ground state that you can construct, and that was the beginning of the matrix product states that have been used so much, and including now in quantum computation and to understand entangled states and so on. It's been a really essential thing. And they proved exactly these properties that Haldane predicted, namely that this is a chain that has a unique ground state of thermodynamic limit, and there's exponential decay of correlations, and there's a gap above the spectrum. So in this point, we know that this prediction of Haldane really holds through. So then you can go on. Let's see what happens if we increase the angle further, and we go to this point here. The gap closes. There's a phase transition. Actually, it turns out to be a point of enhanced symmetry, the SU3 symmetry, and Sutherland used it to prove, using the beta ansatz, that this is a gapless situation. So there is a phase transition there, the gap closes. Then there is a phase I won't say much about. It's a gapless phase with long-range correlations or power law correlations and some quasi-periodic behavior. Then we go to the top part here, and another phase transition occurs, and we enter the ferromagnetic phase. So that's again a frustration-free situation. That is, you can satisfy individual interaction terms of the Hamiltonian and minimize their energy just by having parallel spins, having a ferromagnetic ground state. This is easy to prove. And because you break the rotation invariance, the Goldstone theorem immediately tells you this will be a case where the spectrum is gapless. So above the ground state, you have excitations described by continuous spectrum. They are spin waves. They're easy to construct. So this is well understood and has been well understood for a long time. And you don't see any difference between spin 1/2, 1, 3/2, or anything. So then another phase transition occurs at this angle here. And we enter this yellow phase, which is what I really want to talk about today. And there is, in fact, also an exactly solvable point that was discovered by Klümper and then generalized by Ian Affleck and studied again by many, many people. And it has also an enhanced symmetry with a different representation, SU3 symmetry. Can be described, the Hamiltonian is an element in temporal leap algebra, and that, in fact, was used by Klümper to solve it. And there's a lot of interesting things associated with this, but you have to make some assumptions. These arguments that gave the exact solution actually did not really prove that this was the actual solution for things I could explain, but they are not important here. But there has been some interesting progress I will talk about in a second. So this is where dimerization occurs, and I will explain also in a minute what that is. And then again, there is between this phase, which has in fact two infinite chain ground states, to the one where Haldane has his phase with one ground state. There is again a phase transition with the gap closing. That's a beta ansatz solvable model that was discovered, treated by Taktajan, and then further analyzed by Bjoernberg also a long time ago, 1982. So what is this dimerization? What is this dimerized phase?
Right, interrupt just for a moment,
sure.
Bruno. So if you go back to the AKLT part,
yes,
is there a neighborhood of AKLT where we know that that's gapped?
Yes, absolutely.
Okay.
So I will come to that. So that is the question of stability, and it is really an important question, and I will come to that.
Thanks.
So dimerization occurs if the interaction favors strong entanglement between nearest neighbor pairs. And in fact, this model here, if you look at it, the interaction is negative the projection on the singlet state. So the ground state for just two spins is the singlet state, the maximally entangled state. But as I'm sure you know, there is this thing they call in quantum computation, they call monogamy of entanglement. You can only be maximally entangled with one partner. And therefore, this desire to obtain the maximally entangled state sets up a competition between pairings. Are you going to be maximally entangled with your left neighbor or your right neighbor? And so this naturally often leads to an instability, and in some cases, and in one dimension quite easily, to spontaneous breaking of the translation invariance. Because once a choice has been made, this choice propagates through the whole system. So you have to pair nearest neighbors into maximally entangled states. And it's kind of clear, and it's shown here in this picture. For a finite chain, let's say it has an even number of spins, so that everybody can be part of a pair, then the maximum number of pairs will start with a pair, will be of this form. But then depending on whether you have a multiple of 4 or a multiple of 2 only, and not a multiple of 4, the pair 0, 1, for instance, will be part of a pair, and so will be maximally entangled, or it will not be entangled at all if I am in the situation of monogamy. And so if I take the limit over L odd or L even, I will get different thermodynamic limits. This translation invariant model will have two ground states, pure states, and they will consist of maximally entangled pair, but it's a different pairing. And so there is spontaneous symmetry breaking, and we have periodic states instead of translation invariant ground states. So that is dimerization. Now, in this competition, it doesn't have to be a winner take all, and generically it isn't. The actual ground states generically do not consist of maximally entangled pairs. It's just that there is going to be even pairs are more entangled, odd pairs are less entangled, and there are fluctuations. Quantum fluctuations will generically impose that. There could be exceptions, but that's the generic thing, and that's what happens in the ON chains that I will introduce next. If you take the limit n to infinity, actually you achieve that perfect entanglement situation. But with finite n, there are fluctuations. Okay, so just a quick aside, this sort of fits into the study of topological phases, which in one dimension is not particularly interesting, except if you impose a symmetry. And of course, symmetries in physics are everywhere. It's not like imposing a symmetry is necessarily something unnatural. It may be very natural indeed. So this was understood in the last decade, and in fact proved in quite generality recently by Kapustin, Sopenko, and Yan, and Ogata, that for spin chains, you can only have, for a gapped ground state, so if you have a model and it has something like the Haldane phase, say, then you can only have short range entanglement, and topologically there is no non-trivial order. So if you have two models that are in this gapped phase with a unique ground state, one of the implications is that you'll be connecting with a smooth path of Hamilton. You can interpolate the interactions and sort of smoothly go without phase transitions from one to the other. But of course, the dimerization sort of places you already a little bit outside of that because you have two ground states, and they turn out to be gapped, but they're not unique. But in fact, this whole picture changes dramatically when you impose a symmetry. And most phase diagrams of physical systems and spin chains, for sure, they're going to look at will be about families that have certain symmetries. And so this is what the symmetry protected topological phases are all about. And so one reference here is this paper by Pullman, Turnerberg, and Oshikawa, and who introduced this notion and figured out that for spin chains, in fact, you can classify the symmetry protected phases. So if G is a symmetry group and you impose that all the Hamiltonians you look at and the ones that you would use to construct interpolating paths between models all have that symmetry, then you have the possibility of having multiple phases. And it depends on second cohomology of this group of symmetries that you impose. In the case of O3, which is the symmetry of the AKLT model, for instance, this is Z2. That means there is a non-trivial element in this cohomology, and that means that there is a non-trivial symmetry protected phase, which is in fact the Haldane phase. And it turns out, in fact, you don't need that much symmetry to achieve this. A Z2 cross Z2 symmetry is sufficient. It's chosen in the correct way. And this was proved in full detail by Tasaki and Ogata just a couple of years ago. So that's the wonderful world of SPT phases. And I'll come to Tom's question. So we say phases as if they are phases in thermodynamics, and they are regions in parameter space where things behave in a certain way, distinct from perhaps other phases, separated from them by phase transitions. And so, so this question was raised early on, and it turned out to be also not entirely trivial, and has inspired a lot of work. So these regions where you have one or two ground states with a spectral gap above them in Hamiltonian space, where however you define it, They are not isolated points. They are stable in the sense that you can add small changes to your Hamiltonian. They are locally small, but they are everywhere. So it's in principle an unbounded perturbation. But you can show, or you like to show, that the qualitative properties don't change. And if you had a unique gap ground state, you still have unique gap ground states for these perturbed models. If you had dimerization and a gap, you still have dimerization and a gap after you perturb. And so there are now good general theorems that prove this, but only for frustration-free models. That is like the AKLT chain or the toric code model. Or there's a whole models that have a classical ground state. You can perturb those and prove that. There are some technical conditions I'm not going to go into now. So this started with the work by Jarodsky, 2006, and the famous series of papers by Bravi, Hastings, and Mikalakis and Zwolak. There were other papers. There was a very nice series by Fröhlich and Pizzo with a slightly different method. And we recently have a paper where we extend this to the case where you don't assume uniqueness of the ground state, but you still assume frustration freeness. That's a recent work with Sims and Young. So yes, to answer Tom's question, the AKLT point is part of an open region where we have the same properties, that we have a unique ground state with a gap and exponential decay of correlations. And you can give numbers. They're kind of small. They don't reach this point in particular. That's what everybody has been trying to get to with various tweaks, and so far unsuccessfully. On the other hand, in the meantime, there are numerical results that are amazingly detailed that convince you that really this phase is as drawn in that diagram that I showed you. Okay, so as I said, you can relax the uniqueness condition, but not the frustration-free property so far. And of course, this poses a challenge, and this makes this problem interesting. So we're going to be talking about this point and its stability. And it's not frustration-free. So none of these general results apply. So what are we going to do? I'll try to explain. So not frustration-free means that if you look at the ground state expectation of the energy, it's strictly greater than the smallest eigenvalue of the interaction terms. Okay, there's a frustration that prevents you from minimizing the energy locally everywhere, and it has to do with that same competition between entanglement. You would like to fully entangle to minimize the energy, but that's just not possible. Right? So it's clear that this model is not frustration-free. At least this can easily be seen in this case. So how are we going to prove stability? Well, I'll keep you in suspense. So we can prove a nice result about this. But it will be interesting to look at a more general family. And it's often interesting. Not just for the sake of generalizing, but the model is interesting. They show interesting things and you learn new things. And in fact, there is quite a few generalizations of the AKLT model that have been considered in the literature. There's a particular one I want to introduce to you, and they are the ON chains. So the AKLT model has rotation symmetry, which for three-dimensional spins is O3. So for n-dimensional spins, I can similarly look for Hamiltonians that have an ON symmetry. And those are the ones that we're going to look at. And the way to get there is sort of easily seen by rewriting this AKLT Hamiltonian in a different way. And we're going to introduce the swap operator, and didn't define it because it's so simple. So this is the salvo-joint unitary that interchanges two tensor factors. So if you have a pair of spins in the state phi tensor psi, it maps it to psi tensor phi. And then we can do this, look at the spectral decomposition. But it's not quite a spectral decomposition. I'm going to write it. This, of course, commutes with SU2. It has full SU2 symmetry. And if you look at the eigenvalues, okay, they're plus or minus 1 because this is transposition, it squares to 1. And it shows you that so spin 2 vectors in the tensor product of two spin 1s are symmetric. Then the spin 1 vectors is a three-dimensional subspace are the anti-symmetric vectors. And then the spin siglet in the case of three-dimensional spins is symmetric. Right? So we have eigenvalue 1 here, eigenvalue 1 here, eigenvalue minus 1. And you can sort of now reorganize the AKLT Hamiltonian, which I said was proportional to projection on the spin 2 space. So if I take this operator T, I subtract twice P0, then I get P2 minus P1 minus P0. I have the identity, which is P2 plus P1 plus P0. And I get 2 P2. So I divide by 2. So I can write AKLT Hamiltonian as the swap operator minus twice the singlet projection. It's just another way of looking at it. And the singlet state, so as I said, for three-dimensional spins is symmetric between the two spins, right? And here it is, actually. It alternates signs, but it is a symmetric vector. Now, there's something called Takati Decomposition, and you just can play around with it. You can find a basis for any symmetric vector so that it looks like this here. This is the sort of simplest way of writing a vector that is at the same time symmetric between the two and spin factors and maximally entangled. And so we look at this form because it expresses sort of in the simplest way this property. And there's a unitary transformation that takes you. What is that?
Fourier transform.
Well, you could, yeah, it's something like that. You can write the basis explicitly if you like, and you can do this more generally. And so we're going to work with this form. Now, what is obvious, if you look at this, you write the Hamiltonian in this form, and you use this kind of vector, then I can generalize the AKLT model, which is has the coefficient 1 here and minus 2 here, that you can rescale if you want. But I can put arbitrary coupling constants in front of the T and the Q. And that's what I'm going to do. All right. So we do this not just for n equal 3, but with arbitrary n. I take this maximally entangled symmetric vector and the rank 1 projection on it. I call it Q. And we look at this interaction, and it's now obvious from the way it's written that it has an ON symmetry. Obviously, the swap is going to commute with, in fact, any unitary transformation on all the spins, but certainly with ON. And a vector of this form, it's easy to check, is invariant under the natural action. So the tensor product of the natural representation of ON on n spins. And that gives you an ON symmetric family of interactions, depending on these parameters, U and V. And again, overall scale doesn't matter, so we will have a phase diagram that we can show on a circle, and it generalizes what we did for three-dimensional spins. And this was a model studied in detail, introduced and studied in detail by Tu and Zhang in 2008. And they discovered a number of interesting things about it. So I'm not going to tell you everything that is known about it, but mostly focus on what is relevant for us. But so the parameterization is slightly different. So and therefore it looks a little bit different, but still the phase diagram looks the same, and the same phases appear. It depends on n. So the location of some of these points is the same for all n, but there's also points that move around as n changes, right? But you can sort of identify them as having the same behavior. And so this solvable point introduced by Taktajan was generalized by Rashitikin. A year later, you can do it for n-dimensional spins and find a beta ansatz solution. And so this point separating these two phases, in principle, you know exactly where it is. The AKLT model itself, which is a frustration-free model, is generalized to a family of frustration-free nearest neighbor interactions, where we can also find the exact solution of the ground state. We can prove that there is a gap, but we see there that there is a difference between n, even, and n odd. So for the odd n case, generalizing the n equal 3 AKLT model directly, you find a unique ground state with a spectral gap above it and exponential decay of correlations and everything. But for even n equal 4, 6, and so on, you actually find spontaneous breaking of translation invariance down to 2 periodic ground states. Something like dimerization occurs there too. So this phase, I always call it red, but in fact, it's different in nature depending on whether n is even or odd. We are not too surprised because that's what Haldane told us should happen. And also this phase that breaks the translation invariant is also stable. So these properties are not just valid in this point, but in some interval around it. It's this recent work with Simpson Young. So then the point B prime here, u equals 0 and v equal -1. This again is the projection that is unitary equivalent to the negative of the projection of the spin singlet. So that is the Hamiltonian where the spins want to get into a maximally entangled state, but there is this competition between neighbors and it leads to breaking of translation invariance and dimerization. And so up to some details that are have now been settled, but only recently. Affleck predicted all kinds of properties, and it has interesting relations to temporal leap algebra again, and so on. And it has been studied in great detail, and there's a very detailed paper by Nepomniachtchi and Pimenta in 2016, for instance. But there, so this phase here, at first sight, does not depend on n. For all n3 and larger, you have breaking of translation invariance, you have dimerization. And that was actually proved only recently by Eisenman, Dumerilko, and Wartzel in a beautiful paper in 2020, appeared last year. But that's only for that point. And so what we want to do now is to ask the stability question for that point. Can we prove that this dimerized phase is really a phase in the sense it's an open region in Hamiltonian space, or at least on this phase diagram where you have these properties? So that's what we have been studying with Bjoernberg, Muehlbacher, and Ueltschi, and you can find in this recent preprint on the archive, and I'm going to tell you what we proved. Okay, so that's the problem. Is this point stable? Okay, good. So while I'm going to go over these quickly, there's some comments, and I told you this is not a frustration-free model. No general methods applies, and maybe I shouldn't pay too much attention to this. In the interest of time, let's go to the main results. Finally, some results. So here they are. So we are looking at that spin n chain with ON symmetry. It's a interaction UT plus VQ, where T is a swap operator, Q is the projection on this symmetric maximally entangled state. And for concreteness, I don't really have to do this. I will introduce the analogs of the spin matrices for ON. They're sort of generator of fundamental representation of ON. So they're the ON spin matrices. And our first theorem is dimerization. But we can only prove it for U small, so close to the point that has the exact solution, and that Eisenman, Dumerilko, and Wartzel treated, and large. So this is not perfect. This is not really the final answer, but it's nevertheless a nice answer. So there is some n0 if n is larger than n0 and u satisfies this condition, u is small enough. Then if you look at expectations, and you could take another observable, but let's take sort of the analog of the spin operators, and you look at the pair 0, 1 and the pair -1, 0, then there is a strictly difference between the expectation of these operators. So This observable is a translation to the left by one step of this one, but the expectations are not the same. And they are differed by an amount lower bounded in absolute value by some positive constant C, uniformly in the size of the system. And I've written this here already with like this. So there's a way to select one of the ground states by looking at the Gibbs state at finite temperature, inverse temperature beta, and let beta going to infinity. And I can do this in two different ways if I treat the cases of L odd and L even, and they are indeed translations of each other. So there's two partially dimerized states that are translations of each other that have this periodic structure. So that is the theorem that says that we have this dimerized phase for large enough n in a region of small coupling U, which is the small region around this point. So this is stability of dimerization for this non-frustration-free model. And as one would expect, you also have exponential decay of correlations. We wrote it here for the ON spin operators, but in fact, this is true for arbitrary local observables. Their correlation as the distance goes off to infinity vanishes exponentially fast. So in that same regime, for large n and small u, we can prove exponential decay of correlations. And in fact, you can also go into imaginary time, and that's related to the next property, which is the spectral gap. So we can also prove that this model has a spectral gap uniformly bounded below by some positive constant, uniform in the size of the system. So if you look at the two lowest eigenvalues of this Hamiltonian, and you call the difference delta. In general, it's of course a positive number. It depends on L, but it has a uniform lower bound, which we call C here. So again, for n larger than n0 and u not too large, you can show that the ground state, if you go over these even size spin chains, is unique. It's a simple eigenvalue, and there is a gap above it, and it's lower bounded by this constant. So this we have a stable phase where we have dimerization. We have two periodic ground states that have exponential decay of correlations, and there is a gap above them. So these
what
are
about
the yes.
Would you say something about boundary conditions, or are
so I have implicitly picked boundary conditions by choosing chains of even length. And then since I went to the lowering energy, the Hamiltonian wants to entangle spins, they will pair up and you get this picture of dimerization. And in fact, there will be a dimer sitting at the end. And so if I take L even or L odd, I'm really taking different boundary conditions. Because
okay, so but you could imagine putting other boundary conditions on there, but you're just using.
We use these to produce the two pure ground states. We believe these are the only two ground states. For instance, you can consider chains of odd length, and then there will be some free spin somewhere, or I can impose boundary conditions. I will impose a domain wall, but it will not be stable as far as we know. So these are the two infinite volume ground states that you find. But we have, strictly speaking, not proved that. We have proved that these boundary conditions with these limits produce these two states. Good question. Okay. So how do we prove this? Well, we do this using a graphical representation of the partition function. And this was introduced for the ferromagnetic model by Ball and Todt, and then we generalized it to the antiferromagnetic model. And then Daniel Ueltschi generalized it in a way that you can sort of mix ferro and antiferromagnetic interactions, which is what we need here if you want to consider the models that I described. But to explain the representation, let's first look at the case, really that bottom point where u is equal to 0. Where I just have this projection. I don't have the swap operator in the Hamiltonian. Then, as it turns out, and as I just mentioned, the ground state is simple. And so the projection on this ground state can simply be written as the limit beta going to infinity of the Gibbs density matrix, right? If you go to zero energy, you get exactly the projection on this ground state. And if you want to compute expectations, then you can do it in the same way. So if L is finite for a finite system, this convergence is absolutely trivial. So that's what we're going to do. And then everything comes from a representation of this Gibbs factor. And well, I don't know whether it's necessary. You've probably seen in various contexts the space-time path representations of the Gibbs factor or the propagator for the theory. And so this is just another example of this. And the way to derive it in elementary terms, if you want, is you know this formula for the exponential. And the Hamiltonian is minus q x plus 1, this projection summed over all nearest neighbor pairs. So I need to expand the powers of this kind of sum. And if I do it, I will get the enormous number of terms where these operators q are multiplied in different orders. Now, each of these terms can be represented graphically in a very simple way, but what we call a loop configuration. And so let me show this here. Ignore what's written here. I took this from a previous talk where we just discussed a particular model. So what you see here is the spin chain. So this is the spin chain, and this is imaginary time direction. And it kind of is convenient to let it run from minus beta to beta, but in the end, we're going to take beta to infinity. It really doesn't matter. And then what these double bars here represent is the order in which the q x plus 1s for the different pairs, for the different nearest neighbor pairs occur in a particular term in the expansion of this power. So I expand this, I get products of q's. And this is this product here in this case. And if I discretize this fine enough, it will almost never happen that they occur at the same time. And so I can order them, and I have to take the product of these q's in this order, and then compute a trace to compute the partition function. I want to compute the trace of this, which is the trace of this product of q's, and then summed over all these possibilities. But this q, because I've chosen this very simple vector, because this q says it's going to be non-zero only if on both sides, if it acts on vectors where in the spin basis, the labels are the same. And therefore, we've drawn this like this. With these double bars, they say that before and after the action of q, I will have to have the same spin label. And I can connect these by lines. I see these loops. And then if I insert the basis in between them and I compute a trace, the condition will be that wherever I have this loop, I have to have a fixed label of my basis. And otherwise, there's no restriction. And so I will get a weight that is proportional to the number n to the power of number of loops. N is the number of labels I have, the dimension of my spin space. For each loop, I can choose one, and that determines the weight. Well, the Q comes with a prefactor. So it has these matrix elements, but then there is a 1 over n. And so the number of 1 over n's is the number of these Q operators that I have. And so in this loop configuration, I have to count the number of double bars and introduce a factor 1 over n for each of them. And that's why the weight is exactly this. Now you can take the limit n to infinity, and it's sort of a little bit more elegant to do that. Then instead of summing over combinatorially all these possibilities, you're placing these double bars, these rungs at random according to the bag measure. It's convenient to introduce a normalization factor so that in the end I will have a probability measure. And note that these are all positive numbers. I normalize, I get a probability measure. And I can write the partition function as an integral of this weight n to the number of loops minus the number of runs over this probability measure, and that's the partition function of the system. Great. So, and I can do interesting things with that, and there's several papers where you can read about various results that are proved by now thinking probabilistically of what happens with loop configurations. So that's an interesting way to look at sort of the state of a quantum spin system. But we need to generalize this because our interaction is not just minus q. We also want to add u times the swap operator, where u is some not too large real number. And what does the swap operator do in terms of the spin states? It swaps them. And so instead of this symbol double bar for the q's, which was very convenient to compute the trace of products, the swap operator just switches the states. And so I'm going to draw this kind of picture. When in my expansion, where now I have t's and q's and not just q's, and I will have to again compute the trace of arbitrary products of such things. But the trace again is very simple to compute. So now I have loops. I zoomed in a little bit, and this is what I had. These are the q operators occurring here everywhere, these double bars and making loops. But now I also have in between there, not too many, but some t operators that swap the lines. But I still have loops, and I still have a trace that is simply sum over possible labels I can put in these loop consistently. So very little changed. So I have n to the number of loops minus, so there is a 1 over n factor in the q. So the double bars come with a minus 1 over n. So now I have to count the double bars separately from the crosses. The number of t operators that appear, the number of q operators that appear have to be counted separately. And then the t operator comes with a u, and so I have to actually multiply by a weight u to the power the number of t operators that I have. That is the number of crosses that I see in this random loop configuration. Okay, well, that's good. So modify by measure, and I can describe this more general class of models. So there's a few changes, and they're sort of both important, but I won't be able to explain this in detail. But the first thing is that this u is a real number, and we want to both consider positive and negative u. And so this measure is no longer a probability measure. It's a sign measure. I can normalize it, but it has a kind of a totally different meaning. It means that the integral is 1, but there are positive and negative contributions. So that's one important difference. And the other important difference, which maybe I will come to, or maybe not, is that these loops now cross, and that makes it a very different ballgame in the analysis and properties of the analysis of configuration like this. So these are not non-intersecting loops in the plane. They are still closely packed, but they can, in fact, overlap and intersect. Okay, so that's a difference. But other than that, it is still true that I can express my partition function and correlation functions using this loop picture. And I can still, it's still true that the correlation functions, which I'm interested in, they are integrals of indicator functions of certain sets of loops. When this happens, that's a contribution to a certain correlation function. But you have to remember that it's not a probability measure. And so the integral of an indicator function is not the probability of this event. It's some difference in general of positive and negative contributions. And so I gave an example here of one of the correlation functions that we are interested in. So it's connectivity by loops that produces correlations. And there's two kinds of ways that things can be connected by a loop. So for instance, this point and this point are connected by a loop that goes up and then comes down. They're connected from the top. Or they can be connected in a different way. If one of these crosses appears, then you can have points that are connected by something that goes up and down, and then the second point is approached from the bottom instead of the top. And these are different things, right? So these are these two sets of loop configurations. And for instance, the correlation function can be expressed with this measure as the integral over the difference of the characteristic function of these two events. So this is the event that the two spins are connected by a loop that goes like this. And this is the event, if you want, that the 2 points are connected by something like this. So it goes up and then crosses the line and then it comes down. But as I said, it's not the difference of two probabilities. It's an integral of some simple random variable that you have to integrate with this signed measure. Okay. So now I will try to just explain what's the connection with dimerization, and I won't be able to get into the details, but that is the basic tool that we use to prove these main results that I mentioned before. And so when you look at these loop configurations and you know that they really visualize the correlations between the spins, it becomes sort of important to distinguish small loops from large loops. And basically, we have winding loops possibly, but to be proved for beta going to infinity, they become unimportant. Then there are long loops that visit three or more sides, and they will be the fluctuations we need to control. And then there are the short loops, like this here, which really establish maximal entanglement for a nearest neighbor pair. And so there is this regime, that is the one we are studying, where the configurations are dominated by small loops, at least for half of the pairs, and those will be maximally entangled, and then the rest is a perturbation of it. And I can best explain this if I go back to the special case of u equals 0, which maybe I shouldn't do because it's kind of misleading, but this is the picture that we used in a paper a couple of years ago with Daniel Ueltschi for the case u equals 0 to prove dimerization. So then we don't have crosses, we don't have intersecting loops, we just have these loops that arise from the double bar configurations that are just a Q operator. And then what you see is that what larger loops do, they serve, like the red one here, it serves as a contour that separates the configuration of small loops that establish maximally entanglement correlations between nearest neighbor pairs, but these two are out of phase. So you can use a Powell's argument, in fact, based on this, to prove that you have dimerization for n large if u is equal to 0. And it's relatively simple. And it's based on this idea that the long loops are contours separating the two different dimerized phases, which you can clearly see in this picture, right? So this is shifted, this dimerized pattern is shifted with respect to the one that we have outside. Okay. But now we have this crossing of loops and what we're going to do, instead of the Powell's argument, we will have to use a cluster expansion. And the clusters have to be defined carefully, and because it's no longer so clear with crossing loops, if you see lines cross, how they are connected. And so you have to define clusters of loops that I'm not going to try to do here. This slide, in a way, is kind of a big lie. It's quite complicated to do this in a way that you can actually carry out this argument. And Daniel Ueltschi is a real expert in cluster expansions, and we use some of sort of the recent refinements of convergence criteria and so on to accomplish this. And so I'm not going to go into details of this, but we use the cluster expansion to prove that these large loops are fluctuations, and the dimerization pattern survives as long n is large enough and u is small. Okay, I'm not going to say more about this. So this representation in terms of random loops is worked out so well because of the properties of the terms that appear in the Hamiltonian. And I used the ON generalization of the AKLT chain, which had appeared in the literature, people interested in phase diagrams, so that's okay, but it's by no means the only way you could have generalized this model to larger values of n, the spin dimension. for instance, you could have kept this Hamiltonian negative projection onto the singlet state and not done any basis transformation. It's a very natural thing. And then maybe add also the swap as a perturbation. Seems like makes a lot of sense. And it turns out that for Rn, this is actually a unitarily equivalent model. But for even n, it's not. And that's because the singlet state is symmetric only for Rn. It's an antisymmetric state for even n. And it's antisymmetric in the two spins. And antisymmetry is very different from symmetry. And in fact, you can immediately see that these two models with the Q and the P operator, so let's call P the projection onto the singlet state, they are not unitarily equivalent. For a unitary, that is uniform in the chain. But as it turns out, they are equivalent if you alternate unitaries and the identity operator. And so I'm not going to talk about that in detail, but it turns out you can study this model as well. And although you end up studying a model which you can view as a model with a Q operator, and something that is a swap operator with some other spin flip transformation and sign rule. I'm not going to go in detail, but because we had this cluster expansion has its own kind of robustness. And already we had a signed measure. And so we can treat it, in fact, in the same way and prove the same main theorems about this family of models. But I don't have to explain that in detail. My time is up, says Arthur. And so I was going to ask, does the story end here? And unfortunately, it has to end here because time is up. But then, of course, also, no, it does not end here. And I'm sure it will go on for many more years. And these families of spin chains will give us fun and good mathematical results for many years to come, I'm pretty sure. Not all the questions have been answered. Thank you.
Well, thank you, Bruno, for a really beautiful talk, for the pictures. We're having some interesting results, and for getting up very early in the morning to talk to us from California.
Oh, it's my pleasure, Arthur, for organizing this seminar, and really happy to have the opportunity to talk here.
Well, I think there are a lot of questions that you've raised, and we should open the floor up for discussion. Maybe
I'll stop sharing, maybe.
Yes, why don't
see you.
Are there questions, more questions from the floor? Maybe I should start then by asking, do your methods give any insight into the two-dimensional lattice?
Not immediately. So the representation can be developed for arbitrary graphs. Now, if really it's arbitrary, then it doesn't really have a lot of properties that you can use. But maybe you can stick to bipartite graphs, and then it will have some nice properties. But dimerization or something like it occurs. Of course, you can have two-dimensional models where the interaction really wants nearest neighbor pairs to be in a maximally entangled state, and the same issue arises. There is competition. Which neighbor? But the game generally plays out differently. So very often, there's multiple choice of neighbors leads in more fluctuations and in ground states that do not break translation invariance. And sometimes they do, or they partially do. For instance, you may find ground states that have a columnar structure. So translation invariance is broken in one direction, but not in the other direction. And this is of course of great interest. I mean, people study this numerically. There's some rigorous results also, and there's papers by Giuliani and Lieb, for instance, on models that show this kind of dimerized phases. They use reflection positivity. I mean, you will have to find a model where you have an entry point. There's something you can use, because in principle, a lot of things can happen, and the phase diagrams end up being very rich. And so to turn things into mathematical proofs is generally not easy. it turns out that, in fact, numerical work is not easy either in 2 and more dimensions. And the 2-dimensional systems are important. They are technologically important. So a lot of people work on them, and people make a living improving numerical techniques. And there is, in fact, there's a big project where people compete to get the better energies and so on for exactly models like this in 2 dimensions by numerical methods. So the short answer, the honest answer, is that the particular models that the techniques that we used, they work very well in this 1-dimensional context, but in fact not quite as well as we want to. There is obviously limitations. I could only treat, for instance, large n, and we know that this should really be valid for n greater or equal to 3 without exception, which is in the point u equals 0, but Eisenman, Dominil, Copin, and Warsel proved using other special techniques. There you have a probability measure, and in fact it has very special monotonicity properties, and they use inequalities that follow from these monotonicity properties to prove things. But also there, when you go to higher dimensions, all of that breaks down. So that's a whole open area. So I asked whether the story ends here, and I certainly hope it doesn't. And one way it has to go is to 2-dimensional models, for instance.
So anybody who would like to make a comment, it would be nice if you turn on your video so we can see you. And I saw at one point Tom was unmuted. Did you want to say something?
I was going to ask the same question you did, Arthur.
So Alexandro, you've worked on these things. Maybe you have some comment.
I have a question concerning the AKLT model.
Okay.
About numerical works on the estimate of the gap in that region. So can you say something about?
Well, so I mean, the first thing that everybody who's been working on it will tell you that the numerics are so good that in fact you can explore almost all of this red phase that you had there, which is 90 degrees in size and ends at 2 gapless points. And then where the gap disappears, the numerics becomes trickier, but you can get quite close. And so the best methods or the best results are obtained by a method called density matrix renormalization group, DMRG, which in fact owes its effectiveness to the abundance of matrix product states that you can really use. You can think of the method as a variational method using matrix product states, which you can construct explicitly or describe explicitly. And you can efficiently compute them numerically. And they, in fact, are weakly dense in all states. And you can, so there is a whole series of works where people have studied the complexity problem of efficiently approximating states that aren't matrix product states by matrix product states. And this can be done very well in 1 dimension. But this is still being worked on, but so there are algorithms to do such approximations. And so the numerical results for the ground state and also the first excited states, I think, are extremely reliable, and you could almost turn them into a proof. I mean, there are some things that prevent you from doing that easily, but it probably could be done. In the sense of a computer-assisted proof, and if you would use interval arithmetic or something, you could maybe do it. And so the gap is in the normalization that I given, it's about 0.3 something. People think they know it up to 8 or 9 decimal places. But it becomes smaller as you go to the Heisenberg point, but it doesn't appear to vanish until you reach these 2 exactly solvable points that I marked on the phase diagram. So you can have a lot of confidence that indeed this is a gap phase that extends over this full region and nothing in terms of phase transitions or so happens there. But that said, it is also true, and Ueltschi has studied it. The AKLT point, where you have the frustration-free property, there is something special. So the gap seems to behave kind of normally. But if you look at the correlation length, for instance, so you can prove in general, it's also more recent than you would think, but there is an exponential clustering theorem that tells you if you're going to have a unique ground state with a spectral gap, you will have a finite correlation length. All 2-point correlations, any observables decay exponentially with some uniform rate. If you look at this correlation length as it varies in that phase, that seemed to behave non-trivially and has a singularity at the AKLT point. It has not been fully explained. But it's not visible in the ground state itself. It's something that's visible in the excitations, in the correlation functions, if you want. It depends. I mean, it's not a local observable. If you stick, strictly speaking, with the ground state, then the correlation length is itself not a local observable. But there is some kind of singularity there that you can notice. And probably can be explained by crossing of certain eigenvalues in the spectrum, but not the ground states. So, but it would be nice to have, yes?
Does the mass jump? I mean, does it get bigger? No, does it seem numerically? I'm talking about.
It appears to be continuous.
Okay.
And it has an extremal value at the AKLT point. But I don't know whether the numerics are really good enough to tell you exactly what kind of singularity it is. So there's a paper of Ueltschi's where he explores this with some arguments and numerical calculations. It's 2006, 7, 8. I don't know exactly. I think it's in Journal of Statistical Physics.
Thanks.
But it appears to be continuous. In fact, that's another open problem. If you could prove that the spectral gap has to be continuous in some family of models with short range interactions, something like this, you would really think. I mean, when we prove that it's stable and we use expansions and things like that, it seems like we're proving it's continuous or even analytic in some cases, right? But is it in general, is this true that the spectral gap is continuous? And we were only able to prove it semi-continuous. So you can, and in fact, if you include unstable situations, then it can jump. So it is indeed generally it's semi-continuous. Don't ask me whether it's lower or upper, but it can jump down. You know, it can jump up. So you can have a singular point with a gap and they're surrounded by gapless phases, which Barry Simon would immediately tell me whether that's upper or lower, but I have to think too long to figure it out, and probably I get it wrong. But probably in the case where it's always positive, so you are in a region where you know the gap is positive, it's gapped, I tend to believe it should always be continuous, but this has also not been proved.
Are there any other questions or comments? Such a beautiful talk.
I see Daniel tuned in. He was busy earlier this morning. As I said, he was the real expert in cluster expansions, and so all the things related to that I can explain, he would be able to explain to you.
Is Daniel here now?
Yes, I think I saw him briefly, and maybe it was a figment of my imagination. I don't know.
We have to come back. Well, if there's no more discussion, see you next week with Rupert Frank. And bye-bye, bye-bye, bye-bye.
Very good. Good to see you all. Bye, everybody.